Correlation has been defined as the degree of association between two variables, or a measure of the strength of association among and between variables. Correlation is not defined as causation. At the risk of repeating myself, correlation is also known as association. Say, for example, we find that males are more likely than females to classify themselves as better than average drivers. That doesn't mean that being born male causes you to be a better driver. Sorry, guys. But it does mean that there is an association, a correlation, or a relationship between a person's sex and their perception of driving prowess. Another example might be that as number of years of driving experience increases, the number of accidents, tickets, etc. decreases. Driving experience then could be correlated or associated with safer driving, or at least that's what auto insurance companies are banking on. This video will focus on correlation and to a lesser degree regression. In particular, we will examine Pearson's R correlation coefficient with a mention of Pearson's R squared, which is the coefficient of determination. As we said earlier, correlation is a measure of the strength of association among and between variables. You first attempt to answer the question, is there any relationship between two or more variables? You can do this with nominal level variables, such as, is a person's sex related to or associated with or correlated with pregnancy? Now, being female, for example, would not cause you to become pregnant. The two variables are, however, strongly correlated. There is a relationship between them. However, you'll usually find correlation analysis when you are measuring two continuous level variables, such as amount of time running on a treadmill, measured as a continuous variable, and calories burned, also measured as a continuous variable. We use a correlation coefficient with continuous level variables to express the strength of that association. Is the connection or relationship a strong one, a weak one, or is it non-existent? Just knowing that a relationship exists between variables may not be enough. If you want to predict the value for one variable based upon the value of another variable, you will need to use regression analysis. With correlation, we are just looking for an association or a connection between random variables, while with regression, you are looking to see that if you change one variable, a fixed variable, you can predict a change in the other random variable. We use Pearson's R, also known as Pearson's product moment correlation coefficient, for correlation, and R squared for regression. Don't worry right now if you don't 100% understand the difference between the two. Just know that they exist as we move on. Assume that you have a hypothesis that says the number of hours a student studies for a final exam is positively related to the score they will receive on that exam. Two variables, both of which are continuous level variables, number of hours studying and score on the exam. You can calculate a mean on both of these variables. To determine if a relationship exists between hours of study and exam score, you would calculate Pearson's R because it measures the linear relationship between two continuous level variables. They could be gathering interval or ratio level data. If you plotted out the data, there are four types of relationships that could exist. The first is the one you would probably expect for this example, a positive relationship. The more hours spent studying, the higher the score on the exam. There are a few perfect correlations, but many that are close, such as comparing the number of people who go to see a movie and resulting ticket sales. A negative relationship is the opposite. The more hours spent studying for an exam, the worse the score. Or, as a person's age increases, their agility level decreases. A curvilinear relationship might also exist. And for this example, let's change the variables to anxiety level and preparedness for a test. Those who are unprepared for a test may experience low anxiety levels when taking the test. Well, they know that they won't do well, so why sweat it? And those who are really prepared may also experience low anxiety levels. They have it down cold, so why worry? But it's those in the middle who might experience higher levels of anxiety. And of course, there could be no relationship between the two variables. When you finish calculating Pearson's R, you'll end up with values ranging from -1 to +1. The value describes the strength of association between variables. The closer the Pearson's R statistic is to 1, either negatively or positively, the stronger the relationship between the variables. And the positive and negative signs will tell you the direction of association between the variables. If it is a negative number, it's a negative relationship. For example, more hours studying could be negatively correlated with exam scores. The more you study, the worse you do. A positive number would mean that the more hours you study, the better you would do on the exam. But it's important to pay attention to both number 2 and 3 here. A Pearson's R of 0.15 would indicate a very weak positive correlation, while if you calculate a Pearson's R at negative 0.55, that means it's a stronger correlation, but in the negative direction. You may hear Pearson's R and R squared. What's the difference? Pearson's R is correlation, telling you the strength of association and whether it is a positive or negative correlation. R squared then is, very simply, taking the Pearson's R statistic and squaring it. It will always then be a positive number, ranging from 0 to 1.0. This tells you what percent of the independent variable, say hours of studying, explains what happens to the dependent variable, such as exam score. The closer R squared is to 1, the better the prediction. In other words, the better X explains what happens to Y. So R squared then is used for regression analysis. That takes us to the formula for Pearson's R. Notice that you really only need to know the scores for each group and the means for each group. And degrees of freedom, which you need to look up the critical R value on a table to determine if your findings are indeed significant, is the number of observations minus 2. Back to our hypothesis that there is a correlation between the number of hours spent studying for an exam and the resulting score on the final examination. You gather data from 7 students on the hours they studied, which we will call the X variable, and their exam scores, or the Y variable. So the N for each variable is 7. In total, however, you have 14 observations, 7 for the X variable and 7 for the Y variable, and you'll need to know this to calculate degrees of freedom. You can calculate the mean for each set of numbers. So for hours studied, 2 plus 4 plus 5 plus 7 plus 3 plus 1 plus 6 equals 28. Divided by 7, which is the N for the X variable, is 4. Do the same thing for exam scores, the Y variable, and you'll come up with 60 as the mean. So the mean of X is 4 and the mean of Y is 60. So now we have all we need to start doing our calculations. Look at the numerator of the formula, the sum of each score in the group minus the group mean. You do this for the scores on the X variable, number of hours, and the Y variable, score on the exam. So starting with X, 2 minus the mean of X, which is 4, equals negative 2. Then 4 minus the mean of X, 4, equals 0. Continue doing this for all the scores in the X group. And then do the same for Y. 58 minus the mean of Y, which is 60, equals negative 2. Then 32 minus the mean of Y, 60, equals negative 28, and so on. The formula tells us to multiply these two scores together. So you have negative 2 times negative 2, or 4. Then 0 times negative 28 is 0, and then so on. Sigma tells us to add all of these products together, which is 142. That means that 142 is what goes into the numerator of this formula. Now on to the denominator, which tells you to square the result of each score minus the group mean. Go back to this column. Negative 2 squared is 4. 0 squared is 0, and the rest of the X scores. Sigma again tells you to add all of these numbers together, and we will get 28. You do the same for the Y scores. Negative 2 squared is 4, negative 28 squared is 784, and so on. Add them all together, and you get 1864. Now you have all of the data for the denominator. Now it's time to finish off the formula. Just a review of the formula and what we've calculated already. First, we have the sum of each score on the X variable minus the mean of the X group, multiplied by the sum of each group on the Y variable minus the Y variable's group mean, so 142. You've calculated the sum of each score minus the mean squared for each of the two variables, X and Y. Plugging that into the equation is 142 divided by the sum of the square roots of 28 and 1864, which is 5.29 times 43.17, or 228.46. Reducing that down becomes 142 divided by 228.46, and finally that tells you that R equals 0.62. What this tells you is that as 0.62 is close to the positive 1.0, it appears to be a very strong positive correlation. It appears then that the number of hours spent studying for an exam is positively correlated or connected to the exam score. But now we have to take the next step to compare our calculated R of 0.62 to determine whether we should accept or reject the null hypothesis. And for that, we'll need our critical value table for Pearson's R. First, we need to calculate degrees of freedom, which is n minus 2. Remember that we had 7 sets of scores, 7 scores on the x variable and 7 on the y variable, for a total of 14 scores. 14 minus 2 equals 12 degrees of freedom. And you'll recall that degrees of freedom refers to how many ways our data could be combined and still produce the same value for a statistic. Assuming an alpha level of 0.05 for a one-tailed test, meaning that we're only willing to accept a 5% chance of error, we want to be 95% confident, we can look for critical R. Find where 12 degrees of freedom intersect with a one-tailed test at 0.05, and that's 0.457, our critical R value. Remember that if our calculated statistic is equal to or higher than the critical value, you would reject the null hypothesis, while if it is less than the critical value, you would accept the null hypothesis. In this case, 0.62 is greater than the 0.457 critical value, meaning that we reject the null in favor of the alternative hypothesis. We would conclude then that we're 95% sure that the number of hours studying for an exam does, in fact, positively correlated with scores on the exam. Now, we talked earlier about R squared, which is Pearson's R squared. And this refers to what percent of the independent variable, x, or in this case the number of hours studying, explains what happens to the dependent variable, y, or score on the exam. And in this case, it looks like this positive correlation explains about 38% of the variation. Remember that the closer R squared is to 1, the better x explains y. Processing time. Pearson's R is used to determine if a correlation exists for what type of variables. It is looking for a relationship between two continuous level variables, such as time spent on a treadmill and calories burned. Which of the following indicates the strongest relationship as measured by Pearson's R? 0.12, negative 0.68, 0.50, or negative 0.08? Well, now remember that Pearson's R ranges from a negative 1.0, which is a perfect negative correlation, to a positive 1.0, a perfect positive correlation. The closer the statistic is to 1, either on the negative side or on the positive side, the stronger the correlation or relationship. So of these, negative 0.68 represents the strongest correlation, and negative 0.08 represents the weakest. What is the difference between Pearson's R and R squared? Pearson's R is looking to determine if a relationship exists between two variables, and if so, what type of relationship. R squared, used for regression analysis, is the Pearson's R statistic squared, used to estimate how much of the independent variable explains what happened to the dependent variable. Or put another way, what percentage of the variation in the score on the dependent variable can be explained by the independent variable? And finally,